How can individuals detect, decontaminate, and safely maneuver through areas plagued by invisible yet lethal chemical hazards, even when the fundamental physical laws governing exposure and diffusion seem, in theory, to be controllable? In idealized scenarios, toxic chemical spills are treated as predictable events where known equations of diffusion and dispersion govern the spread of contaminants. Classical models indicate that if one could precisely chart every molecule of a toxic agent, then, with sufficient information and control, it should be possible to pinpoint safe zones, implement targeted decontamination, and retrace the path of contamination back to a pristine state. Yet, in practice, once a toxic chemical infiltrates an area, the spread and persistence of the hazard defy our most carefully planned responses. So far, so good, until we examine the reality on the ground. The toxic chemical spill zone survival challenge emerges when the theoretical reversibility of diffusion and decontamination intersects with the overwhelming complexity of environmental dynamics, sensor limitations, and unpredictable human and chemical interactions. Under ideal conditions, if every toxic molecule and every contaminant flux could be accounted for, safety protocols would be executed flawlessly, enabling the recovery of a clean environment. However, real-world spill zones rapidly evolve into chaotic domains where invisible threats proliferate through unpredictable diffusion routes and persistent contamination shortcuts. One striking example lies in the detection of chemical hazards. Advanced sensor arrays relying on infrared, electrochemical, or spectroscopic principles promise to monitor toxic plumes with precision. Yet, just as light particles find unexpected quantum paths to bypass classical energy barriers, toxic agents in a spill can exploit microenvironments and transient air currents that render detection patchy and incomplete. Much like a drop of dye irreversibly dispersing in water, the hazardous chemicals diffuse into myriad microdomains, often evading even the most sophisticated detection systems. At even finer scales, the situation becomes more intricate. In environments where countless interacting variables, ranging from temperature gradients to surface irregularities, come into play, the spread of a toxic substance is not a straightforward, uniform process. What would appear in simplified models as a neat, reversible plume of contamination instead transforms into a sprawling, statistically governed cascade. Here, the potential configurations for the toxin's distribution multiply astronomically, favoring a state of pervasive hazard that classical monitoring would underestimate. And then there is the critical matter of decontamination. In an idealized setting, if every contaminant molecule were known and its interactions fully mapped, decontamination protocols would neutralize hazards in a single reversible step. In reality, however, minute perturbations, whether from uneven application of neutralizing agents, unexpected chemical reactions, or environmental interferences, prevent a clean reset. These variations, akin to the slightest disturbances in a stirred fluid that prevent the reversal of mixing, ensure that once contamination sets in, it continuously challenges our efforts to reclaim a safe state. Even under controlled conditions in high-tech decontamination units or in specially designed response teams, environmental fluctuations and the inherent instability of toxic materials demand a level of redundancy and probabilistic planning that goes far beyond classical expectations. The seemingly impossible shortcuts taken by hazardous chemicals underscore a fundamental fact. While our theoretical models of contamination and recovery are built on reversible physics, the chaotic and statistically overwhelming reality of spill zones leads to an effectively irreversible spread of risk. So what is truly occurring? This survival conundrum does not imply that the laws of physics, those governing diffusion, chemical reaction, or decontamination, are flawed. Rather, it highlights the limits of applying these idealized reversible models to environments overwhelmed by the complexity of real-world interactions. The notion of a simple controllable hazard clearance emerges from models that assume perfect detection and immaculate decontamination, neglecting the chaotic impact of microenvironmental fluctuations, sensor limitations, and non-uniform chemical behaviors. In actual spill zones, the collective behavior of countless interacting elements overwhelmingly favors a state of continued hazard, rendering contamination both persistent and difficult to reverse. The toxic chemical spill zone survival challenge serves as a potent reminder that while our fundamental physical laws suggest reversibility and control, the high-dimensional dance of molecules, environmental variables, and human factors drives a macroscopic reality where contamination spreads and lingers. It compels us to rethink the relationship between idealized safety models and the entropic, probabilistic nature of chemical hazards, urging the development of richer, more adaptive strategies that can contend with the surprising and often irreversible shortcuts taken by toxic chemicals in complex, real-world settings. The concept of toxic chemical spill zone survival confronts the critical challenge of managing areas contaminated by hazardous substances that are both invisible and highly lethal. While traditional hazard management may rely on observable cues, these zones demand an intricate interplay of advanced detection, effective decontamination, and strategically planned movement. Example, in the event of a chemical plant accident releasing a colorless, odorless toxin, standard sensory detection fails, necessitating high-tech equipment to locate and map hazardous regions accurately. Analogy, it is akin to navigating through an invisible minefield without the ability to see the mines. One must depend on specialized instruments to safely plot a path through a landscape riddled with hidden dangers. Traditional emergency protocols often assume that hazards can be perceived and responded to in a straightforward manner. In contrast, toxic spill zones present hazards that evade direct human detection and require a multi-tiered approach. The process involves identifying the toxin's presence and concentration, neutralizing or mitigating its harmful effects, and establishing safe routes for movement through affected areas. Example, a spill might involve toxic gases that spread rapidly. While visual cues are absent, sensor arrays and remote monitoring systems identify concentration gradients, prompting immediate decontamination and controlled access pathways. Analogy, imagine trying to see invisible ink on a page. Without special light or chemicals to reveal it, the message remains hidden. Similarly, without advanced technologies, the invisible chemical hazards remain undetected and uncontrolled. On a microscopic scale, the behavior of toxic chemicals is governed by diffusion, chemical reactivity, and molecular interactions that defy simple visual detection. These substances can disperse rapidly and interact with environmental factors such as temperature, air currents, and surface materials, all of which influence their spread and persistence. Example, volatile organic compounds, VOCs, released in a spill disperse through diffusion, with molecular interactions causing uneven concentrations that require sophisticated instruments to detect accurately. Analogy, this process is like trying to follow the erratic path of smoke rising from a fire. Although each molecule follows deterministic laws, the collective behavior results in a dynamic and often unpredictable pattern that is not visible to the naked eye. The survival strategies in toxic spill zones rely on rapid identification and neutralization of contaminants. Advanced sensor technologies, ranging from spectroscopy-based detectors to drone-mount sensor arrays, provide the necessary data. Coupled with chemical and physical decontamination methods, these systems address both immediate threats and long-term contamination. Example, in industrial spill incidents, portable mass spectrometers quickly analyze air samples for toxic compounds, triggering immediate decontamination protocols such as chemical neutralization or physical removal of the contaminant. Analogy, it's like having an expert sniffer dog that can detect even the faintest trace of a hidden scent, combined with a specialized cleaning crew that quickly removes the odor before it spreads further. Toxic spill management is intrinsically multidimensional. It involves understanding the spatial dispersion of chemicals as well as temporal changes in concentration levels. Real-time monitoring systems and dynamic modeling allow responders to predict shifts in hazardous zones and adjust decontamination and evacuation strategies accordingly. Example, computer simulations based on real-time sensor data can map three-dimensional toxin plumes, guiding responders in real time as wind patterns or temperature changes alter the hazard landscape. Analogy, consider planning a route through a city with constantly shifting traffic conditions. Even if the roads are clearly defined, Real-time updates and alternative routes are essential to avoid unexpected delays or hazards. In any large-scale toxic event, the detailed information about the initial distribution of the contaminant may become obscured by interactions with the environment. Just as in complex chemical reactions, the multitude of micro-level events leads to an effective loss of detailed information, making predictions challenging. This statistical complexity mandates that hazard mapping relies on probabilistic models and redundant detection systems to ensure safety. Example, during a spill, the chaotic movement of toxic vapors combined with environmental turbulence makes it nearly impossible to reconstruct the exact initial contamination map, leading to reliance on statistical probability to forecast safe zones. Analogy, this challenge is similar to trying to determine the original order of shuffled cards in a massive deck. While the outcome is governed by deterministic shuffling rules, the sheer number of possibilities makes it impossible to trace back to the original order with complete certainty. Understanding the dynamics of toxic spill zones has broad implications for designing emergency response protocols, public safety measures, and urban planning. By integrating advanced sensor networks with real-time data analytics, safety teams can not only respond more effectively to hazardous events, but also plan infrastructure that minimizes exposure risks. Example, emergency management systems that integrate drone surveillance with ground-based sensors can quickly establish safe corridors for evacuation and direct decontamination efforts, greatly reducing potential casualties in the event of a spill. Analogy, it's akin to installing a sophisticated security system in a bank. The system not only alerts you to intrusions, but also provides a coordinated response that protects both the building and its occupants, even when the threat is not immediately visible. One of the greatest challenges in toxic spill management is the unpredictability inherent in the dispersion and persistence of chemical hazards. Even with advanced computational models and detection systems, minor deviations or unforeseen environmental factors can result in significant differences between predicted and actual hazard distributions. This complexity makes it extremely difficult to completely control or reverse the contamination process once it begins. Example, in past chemical spills, sudden changes in weather conditions, such as an unexpected gust of wind, have altered the toxin's path dramatically, necessitating rapid adjustments to previously planned decontamination and evacuation routes. Analogy. This predicament is much like attempting to predict the exact path of a paper airplane in a storm. While the initial conditions are known, unpredictable gusts of wind can easily divert it from its intended trajectory, making a perfect reversal of its course practically impossible. Advances in sensor technology, robotics, and data analytics are paving the way for revolutionary changes in how toxic chemical spills are managed. Future research is expected to focus on developing nanoscale sensors for unprecedented detection sensitivity, autonomous robotic systems for safe decontamination, and enhanced predictive models that integrate complex environmental variables. These innovations promise to transform emergency response and public safety in the face of chemical hazards. For example, emerging integrated systems that employ real-time 3D mapping of chemical plumes, combined with AI-driven decision support, could allow rapid establishment of safe zones even before the full extent of a toxic spill is understood. Analogy, it's like upgrading from a static paper map to a dynamic live GPS system that not only shows your current location, but also predicts traffic, weather, and road hazards in real time, fundamentally changing how you navigate and respond to challenges on your journey.